This is HLAA, Vectors, day number 7, Equations of Planes. Some very typical ways to name a plane. Before we get into this, let's say we have a surface here. Typical ways to name this plane are pi k, right, using some integer value, right? Planes come in one of three forms. They can come in vector form, okay, just as we talked about with lines. They can come in parametric form, and they can come in Cartesian form. Okay, the conversion from one to the other to the third, and the use of those to find points of intersection or lines of intersection are what we're going to cover today. So let's go ahead and get started. Okay, if a point P lies in the same plane as A, B, and C, so take a look at this diagram here. I got point A, point C, point B, and then there's some point P. Typically, we refer to this point P as an unknown point. Right? We refer to it as X, Y, Z. You'll see that show up here in the formulas given below. Okay, so let's assume we know the coordinates of A, B, and C. Well, we can find direction vectors U and V to get us to B from A and to C from A. Now to get to P from A, we can actually use parameters on the vector from A to B, which we call U, and the vector from A to C, which we call V. So we could take, it looks like I could almost use AB at its parameter right now, and then take C maybe more than one step to get to P. Or maybe I have to go a little bit beyond B. So let's say lambda is the parameter for AB. So if I took, I don't know, lambda equals 1.1, and then mu, which is the parameter of V, maybe that had to equal 1.6. And therefore I could find any point on this plane P, right, generally speaking. So let's talk about the three equations. Right, of course, the vector to get from A to P is some parameter times AB plus some parameter times AC, where lambda and mu are in the real numbers. The vector equation of the line, or excuse me, of the plane, would be x, y, z, which are the values or the points for the ordered pair for P, minus the ordered pair for A, which will equal lambda times u plus mu times v. That's no different than this, right? To find a vector from A to P, I take all the points of P minus the points of A. That's what I've got here. We're calling AB this vector u. We're calling AC this vector v. Or this can be written in the following form. Typically, many times planes can be also referred to as this variable r, which is equivalent to calling it xyz, which would be the points of A plus lambda times the vector u, direction vector u, plus mu times the direction vector v. So how do we put this into parametric form? Well, very similar to what we did with lines, we're going to take the components of this location P, x, y, z, the components of A, which is kind of like you could consider that your starting point, and then we've got two vectors with parameters attached that send us to each of those individually. So of course you could see x is equal to a1 plus lambda u1 plus mu v1, y is equal to a2 plus lambda u2 plus mu v2, and then z accordingly. Now the Cartesian equation of a plane, there is no attachment of A, B, and C to the A, B, and C above, right? They don't have any relationship to that. These are values that we'll end up coming up with, and of course this value D in a slide coming up here in a few minutes, okay? So please don't think that A, B, and C are anyhow related to the A, B, and C you see above. Okay, let's go ahead and get started with a few examples. Okay, our first example is very simple. It's to find the vector, parametric, and Cartesian equation of the plane that passes through these three points, right? So we're going to put these 3 points on a plane and come up with the equation in 3 different forms. Okay, so let's place A here. I don't know if the orientation of this will be perfect, but just so we can visualize it, we'll put C up here, and we'll put B down here. Okay, so this would be the vector AB, this would be the vector AC, and of course we're going to place a point out here, we'll call it P. Okay, so from the previous slide, what we saw for finding the vector equation of the line, right, right, is we wrote that R equals A plus lambda U plus mu V. Well, U, we're going to say, is equal to AB. So we have to come up with a direction vector for this particular vector AB. Okay, so U will equal, direction from A to B is the points of B minus the points of A. So that'll be a 1, a 2, excuse me, a negative 2 and a negative 2. I took the points of B, which are 2 minus 1, 0 minus 2, negative 1 minus 1, and I get that vector. Okay, V is going to be the vector from A to C. Okay, so V will equal a 2, a negative 3, and a negative 1. Okay, now R is the coordinates of P, right? So R is going to equal x, y, z, which will be equal to the points of A. This A, vector A, is really from the origin up to A, right? And the origin up to A will be the points of A minus the points of the origin. So there's no change there. Okay, so that'll be the points of A, 1, 2, 1, plus lambda times U, which we determined over here, plus mu times V. Of course, we're under the assumption that lambda and mu are just real numbers. Okay, so there you go. You got the vector equation of the line. Let's put this in parametric form. Pretty simple. So here's vector form. Let's put it in parametric. Okay, so that was part A. Let's do part B. Very simple for parametric. Just align the components. Okay, there's my x equation for the parametric. Put my y equation. Oops, that should be a minus 2 lambda minus a 3 mu. And our z equation will be 1 minus 2 lambda minus mu. Okay, there's parametric. Okay, so let's work on finding the Cartesian equation. And very similar to when we work with lines, it's beneficial to have the parametric form in place in order to do this. So what I'm going to take is I'm going to take my x component and my y component, and I'm going to end up eliminating one of the parameters. Okay, so here I think it would be easiest to eliminate lambda. Okay, and I'm going to end up doing that same thing with two of the other matched components. So for example, I'm going to take y equal to 2 minus 2 lambda minus 3 mu, and z equal to 1 minus 2 lambda minus mu. Okay, so I'm going to eliminate lambda in both of those. Okay, so in order to do that, in the first, I'm going to multiply my x component by a positive 2. That gives me 2x is equal to 2 plus 2 lambda, exactly what I want, so I can eliminate that, plus 4 mu. Okay, I'm going to combine these two equations. Okay, with addition, that'll give me 3x plus y is equal to 4. Lambdas reduce to 0, plus mu. Okay. Over on the other side of things, I can eliminate lambda by multiplying either one of those two equations by a negative 1. I'm going to choose to do that to the first. Multiplying this by a negative 1, I get negative y is equal to negative 2 plus 2 lambda and plus a 3 mu. Okay, I combine my equations here. I get z minus y is equal to negative 1. Lambdas reduce, and I get plus 2 mu. Okay, so now I'm going to eliminate mu. Okay, so I'm going to stack these. This is 3x plus y is equal to 4 plus mu. And you could do this elimination process however you'd like to. I'm choosing to do it this way, aligning the components. And I'm going to multiply this first equation by a negative 2. All right, result of that is negative 6y minus, negative 6x minus 2y equal to negative 8 minus 2 mu. And you can see that our component will set up nicely for eliminating the parameter mu. Okay, so what do I get? I get negative 6x minus 3y, right? I'm just adding like components, plus z is equal to -9. Now typically, like this value here, right, we've seen the Cartesian equation look like this. There's really no preferred form. I prefer typically to have this d value, this constant d, to be positive. It's really not necessary. Either of these two work out. When d is positive, later on you'll see that that's actually beneficial. But this would be the Cartesian of the equation for that plane. All right, let's continue. Okay, so interesting and important topic here. Not really an example to work through. And actually, this is in the wrong place. That's not supposed to be there. But the relationship between lines and planes. Okay, and then we're gonna set this foundation of the relationship between lines and planes, because then we're gonna talk about the relationship between planes and then the relationship between the intersection of planes, which is either a line, a point, or it doesn't exist. Okay, so the relationship between lines and planes, our first example, and this can come in many forms, is that a line fits within a plane, right? It is in a plane. So here's my plane. Let's call it pi 1. Here's my line. Let's call it L1. And all of the points in L1 satisfy pi 1. Okay, so that's a line in the plane that has an infinite number of common points. All right, our second scenario is a line intersects a plane at one common point. So let's take a plane, let's call it pi 2. And we'll take a line, and let's say that line intersects the plane. Right, here's L2. All right, so the point of intersection we can clearly see is right here. Now the angle between the line and the plane, right, is dependent on clearly the line, right? So that could be an acute angle. You could consider the other angle the obtuse angle. You could even have a line, let's call it L3, that is perpendicular to the plane, right? That's called a normal line. So we would technically call this the normal for pi 2, right? So we could have one point of intersection with a line and a plane. That's possible. The third scenario, and very clearly, is that you could have a line and a plane be parallel. So I'm actually going to draw the plane as if we're looking at it as if it looks like a line, really. So I'm looking at the side profile of that plane, and here I've got myself a line. We could call it L3, and there's no intersection of the plane and the line. Now what would that look like from above? Okay, so let's say we're looking overhead on pi 3, and L3 is beneath and never intersecting pi 3. So just an overhead view and a profile view there for you to help. Okay, let's continue on to the next slide. All right, guys, so now let's talk about the relationship between two planes. Now in 3 dimensions, two distinct planes have very similar relationships to two distinct lines in 2 dimensions. So when we talked about lines in 2 dimensions, what we talked about was concurrent, parallel, and intersecting. Okay, and that intersecting could be at an orthogonal right angle or otherwise. Okay, so let's sketch 2 parallel non-concurrent planes. Okay, so let's consider the profile view of pi 1 and pi 2. Okay, so imagine this plane that extends off in all directions, right? Those would be parallel. Okay, let's try to imagine it with a little bit more perspective. Okay, so here's pi 1. Okay, and then here is pi 2. Right, and pi 1 and pi 2, they never intersect, and therefore they would be parallel. Okay, and non-concurrent. If they were concurrent, of course, those 2 planes would be the same. They would contain all the same points, infinitely many, forever. Okay, let's sketch some intersecting non-orthogonal planes. All right, so let's go pi 3. This is a little bit more interesting to sketch. You'll see why in here in just a second. Let's intersect these two planes. Oh gosh, that's pretty decent. Okay, you can see my dotted background version, and the Packer fans out there are loving this apparently. Okay, these two planes intersect, and they intersect at a line, right, L1. Okay, so pi 3, pi 4, they intersect at a line. Now the angle between the planes, right, this angle theta and this angle, let's call it phi, those add to 180. All right, so theta plus phi is equal to 180. All right, let's sketch orthogonal planes. All right, so let me sketch a plane here. Let's call it, I don't know what I'll call it yet, but we'll see it here in a second. Oh gosh, I'll go downward with it, there we go. Let's call this, let's just say for the sake of simplicity, that this one plane doesn't extend above the other. All right, so here I've got orthogonal planes. What does that mean? That means the angle between the planes is 90, right? So you can imagine a 90 here as well. All right, so here I've got, we'll go green again, pi, we'll call this pi k, and we'll call this blue one pi l. All right, so pi k and pi l intersect at a 90-degree angle. Of course, those two intersect at a line as well. We could call that L2. Okay, what's interesting about all of these situations is that when we talk about parallel non-concurrent planes, or we talk about intersecting orthogonal planes, or we talk about orthogonal intersecting planes, there's a special relationship between the normals. So here, let me draw pi 1, pi 2, and their normals. Here is a normal to pi 1. Okay, right? 90-degree angle there. Okay, here is a normal to pi 2. Again, a 90 here. Since those two lines are parallel, what's true is that k times the normal of pi 1 is equal to the normal of pi 2. Just meaning, right, that those two are parallel vectors. Very interesting. Okay, let's look at the intersection of pi 3 and pi 4. We'll just look at the acute angle here. Okay, let's sketch a normal from pi 4. There's a normal from pi 4 and a normal from pi 3. This would be the normal from pi 3. Oops, not pi over 3, just pi 3. Okay, and the angle between them, that angle there, and this angle right here, add to 180. So let me call this angle, I don't know, let's go psi, something like that. That's a Greek letter. Plus gamma, which is this angle right here. Those should add to 180. So the angle between the vectors, the normal vectors, is supplemental with the angle between the planes, right? So this is our angle between the normals, this is our angle between the planes, and those are obviously supplemental. Okay, one more interesting sketch here with the orthogonal intersecting planes. So here's pi k, and here is pi l. Here's a normal to pi l. And here's a normal to pi k. Now, those don't have to intersect, but we do know that those normals would be perpendicular to each other. Very interesting. Okay, we're going to encounter a few items with that coming up, not this lesson, but the next. Okay, let's go ahead and move on. Okay, so I'm going to give you a little trick here, which is going to be maybe a little premature, but it is going to be very, very helpful, okay? And it's going to help you specifically with part A in this particular problem. I kind of waffled on whether or not I was going to show you this yet, but I think I'm going to do it because it is so convenient. Okay, so given the following planes, I got pi 1, pi 2, pi 3. It says in part A, show that pi 2 and pi 3 are parallel. Okay, so we talked about what it means for two planes to be parallel, right? So here's pi 1, excuse me, I want pi 2. I want pi 2 to be parallel to pi 3. Okay, when we sketched out two planes, okay, with their profile view, pi 2 and pi 3, what did we say about their normals? We said the normals were parallel to each other. So what that meant was that k times the normal vector, direction vector of pi 2 is equal to the normal vector of pi 3, right? Some constant times one of the normals would be equal to the other normal. Okay, now how do I identify a normal, right? So this is what I was kind of waffling on, but the normal of pi 2 is going to take on the values of the coefficients of x, y, and z. And that always is always true, right? So you can see for pi 2, I've got coefficients of 1, 2, and negative 1. Okay, the normal of pi 3 is identified by the same method, right? So 2, 4, and negative 2. Therefore, since it looks like 2 times the normal of pi 2 is equal to the normal of pi 3, then we know that pi 2 is parallel to pi 3. Okay, pretty easy there once we know kind of that niche, right? How to find the normal direction vector based on the Cartesian equation of a plane. Okay, now in part B, we've got a little bit of work to do, right? We are told that pi 1 and pi 2 intersect, and that we want to find the equation of the line of intersection of those two. Okay, so this is going to take a little bit more work, some algebra. Okay, so pi 1, I can see is 2x minus 3y plus 5z equal to 1. Pi 2, x plus 2y minus z is equal to 0. Okay, so the first thing that we want to do is we want to isolate a variable, and I'm going to do that in pi 2. I'm going to isolate z. Z is going to equal x plus 2y. And I'm going to use that, and I'm going to plug that in for z in the other equation. Okay, so our end result is to isolate the variables so that I've got what you'll see here in a little bit is I'm able to find the Cartesian equation of the line. Okay, so I'm going to go from Cartesian form of the plane to Cartesian equation of the line. So I'm going to take this, x plus 2y, and I'm going to plug it in for z. Okay, so I would have 2x minus 3y plus 5 times that quantity will equal 1. Okay, so let's continue. Let's do a little algebra here. That will be, I'm going to get a 2x minus 3y plus 5x plus 10y is equal to 1. Therefore, 7x plus 7y is equal to 1. Now what I want to do is I want to isolate y, right? I'm going to isolate y and I'm going to plug it back in here so that I'll have y in terms of x and z in terms of x, which will allow me to write the Cartesian equation of the line of intersection. Okay, so I'm going to solve, so that would mean that I would subtract 7x and divide by 7. So I would have y equals 1 minus 7x all over 7, which I'm going to write as y equals 1/7 minus x. Okay, so there's y. Okay, I'm going to plug that back in over here, like I had mentioned. So z is equal to x plus 2 times y. I'm going to take that expression, 1/7 minus x, plug it in, and I'm going to solve. So z will end up equaling x plus 2/7 minus 2x. Therefore, z is equal to 2/7 minus x. All right, so now I can write the Cartesian equation of the line of intersection, right? I'm finding where x, y, and z are equal for these two planes. Okay, so what I'm going to do is I'm going to solve for x in both of these. That's the link between z and y is x. So x is equal to, that would be 1/7 minus y, I think, yep. And x is equal to 2/7 minus z. Okay, so let's put this in Cartesian form for a line. So x is equal to 1/7 minus y, and z is equal to 2/7 minus z. Now, if you want it in the traditional form, right, where you have, you know, z minus a over b, that sort of thing, or y minus c over d, right, we could rewrite this as y minus 1/7 over -1 and z minus 2/7 over -1. And that'll allow you then obviously to have this line of intersection. So if I have pi 1, pi 2, and I'm not quite sure what this looks like, but if I have pi 1 and pi 2, and this could be totally off from its actual, wow, that was not my best, but that's okay. This line right here is this line right here. Okay, so this would be L1 such that pi 1 and pi 2 intersect. Oh, that's why it was all jacked up. There we go. Okay, cool. That's how you find the line of intersection of two planes. Let's continue. Okay, normal vectors and planes. Since the normal vector n is perpendicular to every vector in a plane, right? So let's take a plane. We'll just call it pi, generally speaking. Okay, and let's draw a normal. Right, here's a normal to the plane coming out of there. There you go, normal to pi. Okay, that normal. My alarm just went off. That was kind of funny. Okay, so that normal, right, we can highlight it. Let's put it in red. Normal pi. Right, that normal is going to be perpendicular to any vector AP, right? Any vector AP. And let's assume we don't know the coordinates of P, but we do know the coordinates of A, right? These two, if I dot them, we should get 0. So we're going to use this idea to write the Cartesian equation of a plane using just 3 points. Okay, so we're going to use just 3 points in a more efficient manner than we did earlier to draw or to write out the equation of a plane. Okay, so here we go. Right, I got my plane pi. I got my points A and C and B. So here's A, here's B, here's C, right? What I can do, as mentioned before, is I'm going to put a point P out here, and I don't know the coordinates of it, but it's going to help me to write the equation of this plane. Okay, so let's take and find AP, right? Let's find AP. What would AP equal? Well, that would be all the points of P minus all the points of A. So that'd be x minus 1, y minus 2, and z minus 1. Right? It took all the points of P, which were unknown values, x, y, z. This gives me the general case. Right, and then now I have this vector AP. Well, how do I find a normal? Because I know that the normal vector dotted with AP should equal 0. Well, how do I find the normal? Well, you can find the normal by taking AB and crossing it with AC. Right, that'll give me my normal vector. And now, what we'll see in just a moment here is that we can utilize that to come up with the Cartesian equation of this plane. All right, so let's find the normal. So AB is going to be all the points of B minus all the points of A, which will be -4. Nope, that's wrong. Let's try that again. 2 minus 1 is 1. 0 minus 2 is -2. -1 minus 1 is -2. Okay, so there's AB. I'm going to cross that with AC. Okay, AC will be 3 minus 1, which is 2. negative 1 minus 2, which is negative 3, and 0 minus a negative 1, which is 1. Oops. When I cross those, or use the vector product between them, I get the normal. And the normal, you can check this on your own, ends up being negative 4, negative 3, and a positive 1. Actually, I messed something up here. That should be a negative 1 here. Okay, cool. So now we have our normal. So our normal is, actually I should do this in black to match. Normal is negative 4 and a negative 3 and a positive 1. We're going to dot that with AP, which is x minus 1, y minus 2, and z minus 1. And that's going to be equal to 0. Okay, so let's go ahead and execute on this. So I get negative 4x minus 4, right? I just distribute negative 4 to x and to negative 1. And that should be actually a positive 4. Good. Okay, that's my first component. My second component will be a negative 3 times y, and a negative 3 times negative 2, which is a positive 6. Okay, you can start to see how the Cartesian equation of this plane is starting to form. And then I'm going to take 1 times z minus 1, which is z minus 1, and set that all equal to 0. Now I'm going to combine my like terms, so I get negative 4x minus 3y plus z, combining negative or positive 4, positive 6, and a negative 1, I get a positive 9. And this, you'll see, actually probably recognized from earlier, is the exact same equation that we came up with on our first slide for finding the equation of that plane. Because remember, I said I prefer that this number is positive, so I get 4x plus 3y minus z is equal to 9. And so given 3 points, you can just use a normal vector, which is the cross product of any two vectors in a plane, dotted with another vector that has an unknown point p, and you can get that Cartesian equation. All right, let's continue. We got 2 more slides. All right, for our last couple of slides here, we're going to talk about the relationship of 3 planes. Okay, so let's look at the possibilities for the intersection of 3 planes. Okay, so you could have, 3 planes, pi 1, pi 2, pi 3, that just don't intersect. And I'm looking profile view here, obviously. You could have, so that's one situation, right? Where non-intersecting, non-concurrent. Another situation could be, for example, 2 planes are parallel and the third intersects those, right? Whether it's at a right angle or not. That's not that interesting either. The third option is that all 3 of the planes intersect. Now there's 2 different scenarios here, okay? And bear with me for a minute. Okay, let's say that, here you got pi 1, here you got pi 2. Well, guess what? When you have 2 planes that cross, you're going to get a line of intersection. Okay, so here's your line of intersection, which we can't see because of the profile view, but let's just call that L. When I throw a third plane in, if the third plane looks like this, we'll call it pi 3, it still is considered a line of intersection. Okay, now with regards to that, what would that look like? Okay, so let me try to sketch this. Okay, and it's going to be kind of messy. We'll see what we can do here. Okay, so there's pi 1. I'm going to keep the other half of pi 1 just for a second. Here's our line of intersection. I'm going to send pi 2 kind of up this way, right, and send them down this way. And I'm going to send pi 3 kind of out this way and down that way. Okay, so it's not perfect, but you can kind of see what's happening here, where these planes are intersecting at that green line. Okay, now let's look at the other option for the intersection of 3 planes. Okay, the intersection of 3 planes that's not a line has to be a point. So let's say I again have, pi 1 and pi 2. And of course, when I have the intersection of two planes, as long as they're not concurrent, that has to be a line. So there's L. Okay, but what if pi 3 looked like this? Now think about that, right? Pi 3 is intersecting pi 2 at an infinite number of locations, but let's think of it like kind of as those endpoints, right? So it's intersecting pi 2 everywhere in here, right? And it's intersecting pi 1 everywhere in here. Well, where is it intersecting both? At one single point, right? Now it's just point A. So that's the orientation for where you'd see the intersection of three planes just being one single point. Okay, so let's get into an example of this. Let's look at the intersection at a point of these three planes. All right, so I'm going to take a slightly different technique here. Prior to, I stacked my equations, I eliminated some variables, and I did some work that way. What I'm going to do is I'm going to find the line of intersection of these two planes, pi 1, pi 2. Okay, so I am going to stack these, right? I'm going to write x plus 2y minus z is equal to 4, and 2x minus 3y plus z is equal to negative 3. Now, why did I choose these two in particular? Because it's actually nice. I can just eliminate z immediately. Okay, so I'm going to add them together. I get 3x minus y is equal to 1. That's going to be useful here in a minute. Now, I'm also going to take the first plane equation, and I'm going to solve for z. Okay, I solve for z, and I say that then x plus 2y minus 4 is equal to z. Okay, so what should I do with this? Well, I'm going to utilize both of these to find the line of intersection. I'm going to solve here, and I'm going to solve for y. Y is going to equal, it looks like 3x minus 1. I'm going to take that 3x minus 1 and I'm going to plug it in for y up in this equation. So I get x plus 2 times 3x minus 1 minus 4. Okay, so z is equal to, it looks like 7x minus 6. Okay, so x is equal to, in terms of z, this would be z plus 6 over 7. Okay, and x in terms of y over here would be y plus 1 over 3. So I can write the Cartesian equation of this line. X is equal to y plus 1 over 3 and z plus 6 over 4. There's the equation of the line of intersection of pi 1 and pi 2. Okay, so how do I utilize that then to find the point of intersection of these three planes? Okay, so what I'm going to do, and this is always very useful, is I'm going to take this Cartesian form and I'm going to put it in parametric form. Okay, so putting this in parametric form, right? Let's say x equals lambda, right? And y plus 1 over 3 equals lambda, and z plus 6 over 4 equals lambda. Essentially what I'm doing is I'm going to solve for x, y, and z, and that'll be my parametric form. So if x equals lambda, then I get 0 plus lambda. If if lambda equals y plus 1 over 3, then y would equal negative 1 plus 3 lambda. And z, of course, in this case, will be negative 6 plus 4 lambda. Okay, so now I have the parametric form for the line of equation, the line of intersection of pi 1 and pi 2. Okay, so what do I do with that? Because I haven't incorporated pi 3 yet. So I'm going to bring pi 3 into the play here. So pi 3 is 3x plus y minus 4z. Okay, and I know that there's a specific point on this line, I don't know what it is yet, but that lies in pi 3. So what I'm going to do is I'm going to plug 0 plus lambda in for x, negative 1 plus 3 lambda in for y, and negative 6 plus 4 lambda in for z. Okay, now think about this for a moment. What am I going to be solving for? I'm going to be solving for the parameter of the line at which the plane is satisfied. So if I can find the parameter, what would that do? I can plug it in here and I can find the point of intersection. Just realized I made a mistake up here. This shouldn't be a 4, this should be a 7. I see it right there now. That was my mistake. So this should be a 7 as well. Okay, so now we do some algebra. We get 3 lambda minus 1 plus 3 more lambdas plus 24 minus 28 lambda, and that's all equal to 1. I'm going to combine some like terms. Okay, so that'd be a positive 23. If I subtract it to the right side, I get a negative 22. Okay, I combine all my lambdas. That's a negative 22 lambda. Nice, so it looks like lambda equals 1. Okay, so we're going to take lambda here, which is the parameter on the line that satisfies the third plane. And I just realized I forgot to change this to a 7. Okay, and we're going to be able to find the point of intersection based on that parameter. We're going to plug it back in for lambda in this parametric equation. That'll be 0 plus 1 for x, and negative 1 plus 3 times 1 for y, and negative 6 plus 7 times 1 for z. That gives us the point of intersection of those 3 planes, x, y, z, to equal 1, 2, and 1. Let's move on to our last example for the day. All right, so this is our last example for this set of notes. It's been quite a lesson. So let's go ahead and get to it. Find the possible values of A, B, C, and D so that the following planes intersect at exactly one line. All right, so not at a point, but at a line. Okay, so I want to find values for A, B, C, and D. So clearly I'm going to do a majority of my work algebraically with pi 1 and pi 2. So let's find the line of intersection of pi 1 and pi 2. We'll use similar techniques to what we did before. I'm going to solve for pi 1. I'm going to solve for y. That'll be negative 2x plus 3z plus 1. And for pi 2, I'm going to solve for x. X will equal 2y minus 2z plus 4. Okay, so now what I'm going to do, this is very similar techniques to what we did before. I'm just going to utilize a slightly different approach, and you can approach this however you'd like to. I'm just trying to show you a variety of approaches. So I'm going to plug this in for x over here, and we're going to do a little work with that. So let's go to it. All right, so y is equal to negative 2 times the quantity 2y minus 2z plus 4 plus 3z plus 1. Okay, so if I simplify this, I get a negative 4y and a positive 4z and a negative 8 and a 3z and a 1. Okay, combining like terms, I'm going to get a 5y on the left, and on the right I'll get a 7z minus 7. Okay, so let's solve for y. Right? Y in terms of z is 7z minus 7 over 5. Okay, that's going to be useful here, as I'm going to plug that into our pi 2 equation solved for x in for y. So I'm going to plug that in right there. Okay, so x is equal to 2 times that quantity minus 2z plus 4. Let's plug it in. 7z minus 7 over 5. All right, so x comes out to, if we solve this, comes out to equal, I believe, 4z over 5 plus 6 over 5. Okay, so I've got x in terms of z. I've got y in terms of z. In order to get the Cartesian equation of the line of intersection of pi 1 and pi 2, since z is kind of the bridge to both x and y, I'm going to solve for z in both. So if I solve for z on the left, I end up getting 5y plus 7 over 7. Okay, and if I solve for z on the right, I get 5x minus 6 over 4. Okay, so now I've got z in terms of y, z in terms of x. I can write the Cartesian equation of the plane, of the line of intersection. And I can put this in parametric form. Let's go ahead and do that. Okay, here comes parametric form. I'm going to solve as if each of these are set equal to lambda. So x will equal 6/5 plus 4 lambda. And I'm going to show you something kind of cool here in a minute, over 5. Y is equal to -7/5 plus 7 lambda over 5. And z just happens to equal lambda. So at this point, now this is very interesting to note. At this point right here, where was I? Here we go. Right? At that point right there, and this point right here, since I have both in terms of z, I actually have both in parametric form already, because I'm assuming that z is going to be equal to lambda. Now, if that doesn't connect up top, just leave it alone, right? Go this direction and come up with the parametric equation of the line of intersection. Okay, now let's try to keep this simple here for just a moment. All right, imagine that this line, right, let me call this, L1. Okay, imagine L1, we're under the assumption that L1 is contained in pi 3, right? Here's pi 3. Okay, if L1 is contained in pi 3, then L1 is perpendicular to the normal of pi 3. Okay, so that means that the direction vector of L1, right, the direction vector of L1, which would be equal to 4/5, 7/5, 1, right? I'm getting that here from our coefficients of lambda. Okay, that direction vector of L1 dotted with the normal from pi 3 should equal 0. Okay, so let's take and let's scale this, right, direction vector to kind of make the algebra easier here, because we're going to have to do a little bit of guess and check. So I'm going to pull out a 1/5, which will make our direction vector for L1 4, 7, and 5. Okay, so this is the direction vector of L1, and we're going to dot this with the normal vector from pi 3. Well, the normal vector from pi 3 is just a, b, and c. Right? We don't know those values yet. Now, the 1/5 here kind of becomes irrelevant, right? All that I want to happen here is that 4 times a plus 7 times b plus 5 times c, I want that to equal 0 in order for this to be true. Okay, so now it's a guess and check game. Now, what I'm going to actually just go ahead and say is to give you the answer. Now, you might have to do a little guess and check, but I'm going to say that A, B, C, right, A, B, C, are going to equal -3 and 1 and 1. Right, because if A is -3, that gives me a -12. B is 1, that gives me a 7. C is 1, that gives me a 5. And of course, that would come out to be 0. Okay, so pi 3 is going to have coefficients of -3x plus 1y plus 1z. Now, I don't know d. Now, this is just one of the possibilities, right? There are other possibilities for these coefficients for pi 3. So we are almost complete. We just got to find a value for d. So what I'm going to do is I'm going to find a point on the line, L1, and that point has to also satisfy pi 3. And that point will be in x, y, z, right, in L1, such that it should satisfy this, and then my only unknown will be d. Now, if lambda equals, let's say lambda equals 1. Let's see what happens in our line here. Okay, if lambda equals 1, it looks like x will equal 6/5 plus 4/5, which is 10/5, which is 2. If lambda equals 1, our y value will be 0. And if lambda equals 1, our z value will be 1. Therefore, this point should satisfy pi 3. If I plug in a 2 for x, a 0 for y, and a 1 for z, we'll find d. It looks like d is equal to -5. All right, so let's finish it off. Pi 3 will end up being or could end up being. This is one of the possibilities. There are others for our coefficients for A, B, C, and D. Okay, should equal this. Now if I follow my rule, I am allowed to multiply by a -1, giving me 3x minus y minus z is equal to +5. All right, there you have it. That's it for today's lesson. I hope it went well. Let me know if you got any questions, and we'll see you in the next video.